Hi. So today we want to discuss for the topic 5 is electromagnetic induction. So before we start to discuss what is electromagnetic induction, so just briefing to all of you. Actually, for this topic, we want to discuss for the production of induced EMF. Okay, basically is produced by the magnetic field. So that's why we can see here magnetic field. Okay, we've produced induced current and also induced EMF. So now look at the subtopic 5.1 is a magnetic flux. What is a magnetic flux? Magnetic flux, this is the symbol of a magnetic flux is equal to vector B dot vector A. So we can apply the equation as a BA cos theta. So be careful here. The angle theta must be between direction of vector B and vector area A. So now I want to show all of you what is a vector A or how to identify the direction of vector A. Let's discuss. For this is the surface, the cross-sectional area or the surface, horizontal surface. So how to show vector A? So vector A must be 90 degrees to the surface. Alright. What about for the second surface, vertical plane? So for the vertical plane, so vector A must be 90 degrees to the surface. So this is vector A. Next, if we have many turns, so so we can write as a magnetic flux equal to N BA cos theta. So N is a number of turns. Now, unit for the magnetic flux in Weber or the symbol WB, and then the magnetic flux is scalar quantity. So refer to the two examples here. So we want to determine magnetic flux. So the green color here is your magnetic field. Right? So this is the cross-sectional area horizontal vertical plane. And this is horizontal plane. So now we need to show the direction of vector A. So this is the surface. So must 90 degree. This is A. Same with the second diagram. This is vector A. So now look at the angle between vector A and vector B. Vector A here and vector B here. So now the angle between them is 0. Therefore, when we want to calculate magnetic flux, B A cos 0. For the second diagram, so we can see here, so this is a vector A, and then this is the direction of B. So angle between them is 90 degrees. So theta is 90. So when we want to calculate magnetic flux, BA cos 90. Next, for the subtopic 5.2, induced EMF. So for this topic, so we have two laws. So for the Faraday's law and the Lenz law. What is a Faraday's law? The magnitude of induced EMF, so this is induced EMF, proportional to the rate of change of magnetic flux. So this is the rate of change of magnetic flux. So now, negative sign. So here, negative sign indicates that the direction of induced EMF always oppose the change of the magnetic flux producing it. Alright. So for the Lenz law, induced electric current always flow in such a direction it opposes the change producing it. Now, we want to discuss a few factors influence induced EMF. Basically, when we substitute for the magnetic flux with NBA cos theta here, so we can see the first factor, induced EMF, directly proportional to the rate of change of magnetic field, directly proportional to the rate of change of area, and angle. So we have three factors influence the induced EMF. To show the application of Faraday's law and Lenz law, so we have three examples. Movement of the bar magnets. First, when the bar magnets move towards, so the keyword is towards the coil. So we can see here, when the bar magnet, this is not the North Pole towards or approach the coil. So what happened? So we can see here, this is the magnetic field produced by the bar magnet. Alright. So the number of magnetic field, so this number of magnetic field that moving into the coil. So this is magnetic flux. So this is the magnetic flux. Okay, what happened when the bar magnets moving towards the coil. First, magnetic flux increase. Okay, so when the magnetic flux increase, so we'll produce induced EMF and induced current. Next, this is referred to the Faraday's Law. When the magnetic flux increase, so meaning induced EMF proportional to the rate of change of magnetic flux. So this situation will apply Faraday's law. Now, when the induced current produced along this wire, so now we need to apply Lenz law. So Lenz law stated that induced electric current always flow such a direction that oppose the change producing it. Now, when the bar magnet moving towards the coil, so we can see here the magnetic flux increase. So from the Lenz law, we need to oppose the increasing of magnetic flux here. We need to oppose the increasing of magnetic flux here. So that's why to show the opposition, so this side must not. Automatically, these sides become south pole. So by using the right hand grip rule, so your thumb will present the direction of the north pole. So we can see here your fingers is downward. So refer to the direction of current. Meaning the current produced here refer to the fingers. Right. So here direction of induced current and the galvanometer here. Next. So for this situation, to show the direction of induced current, so this we call as a Lenz law. Next, what happened when the bar magnet static? Okay, what happened? So induced current equal to 0. So what happened to the galvanometer? Will show 0 volt. Now, what happened when the bar magnet moving away from the coil? So we can see here the magnetic flux will be decreasing. So now, from the Faraday's law, when the magnetic flux decreasing, so will proportional to the induced EMF. This is Faraday's law. Now, any changes, alright, for the magnetic flux will produce induced EMF, meaning here will produce induced current. So how to show the direction of induced current? Okay, the induced current, the direction is always opposite the change producing it. Because of when the bar magnet moving away from the coil, so we can see here the magnetic flux changes, meaning reducing, decreasing. So that's why this side must south pole and then this side must north. Okay. By using right hand grip rule, your thumb will represent knots and your fingers represent the direction of induced current. So we can see here your fingers moving upward. So this is the galvanometer. Okay. So for this situation, okay, so this is to show you the application of Lenz law. Same with this one. Alright. The conclusion is for the case towards, so this side must be same pole. Let's say north must north. Let's say here south, so here must be south. Next, for the case away, if this side is north pole, so the opposite side must south. Let's say this side is south pole, so this side must be north pole. And then use right hand grip rule to show the direction of induced current produced.